really? First time? Or?
I've always been doing that for now a year and a half. Very successful, more and more useful for
I think so, because I just figured out that this one is very short. So about half of the slide. But I'll try to mostly that's a disadvantage of being the first, because you still don't know how.
Yeah, I'm certainly going to take advantage of that, because after your talk, I still have some time.
Right.
Changes in mind.
So I have the
I asked you to give a very general one.
Yeah.
So I have the honor of introducing our first plenary speaker of this colloquium. Our first speaker is Professor Noga Alon. Noga is boundary professor of mathematics and computer science at Tel Aviv University, Israel. He received his PhD in mathematics at the Hebrew University in Jerusalem, 1983, and he had visiting positions in various research institutes, including MIT, the Institute in Princeton, IBM Almaden Research Center, Bell Labs, Bell Core, and more recently Microsoft Research. He serves in editorial boards of more than a dozen international technical journals, has given invited lectures in many conferences, including plenary lectures in 1996 of the European Congress of Mathematicians, and 2002 International Congress of Mathematicians, and an invited lecture in 1990 at the ICM. So he has published more than 300 research papers, mostly in combinatorics and theoretical computer science, and one very famous, very important textbook, text research book in probabilistic combinatorics. He's a member of the Israel National Academy of Sciences since 1997. He received the Erdős Prize in 1989, and the Feyer Prize in 1991, the Poya Prize in 2000, and the Bruno Memorial Award in 2001. Just to close, I'm sorry for the long introduction. So in every subject there is someone, or there are a few people that you very much like and very much revere. And in combinatorics, certainly Noga is one of them. But sometimes he's so perfect that we kind of get annoyed with it, and then we say, well, we know that in school he was a straight A's boy, so he got A's in everything, except in physical education. So he got a C. As far as I understand, so this was his uncle, who said, well, he should get an A, but then he would be too conceited, so I'll give him a C.
Thank you. Don't always believe everything you hear in these introductions, but so it's a great pleasure to be here, and I'm happy also that someone took care of the weather to make sure you are all here, because you can't wander outside. And I speak, the title is Probabilistic Reasoning, and the first part of this lecture is going to be very light. In fact, it could almost be a bit boring for experts. So if you are bored in the first part, that's a very good sign, because it means you are an expert. And the second part will be somewhat more technical. So what I want to stress in the first part is that probability can be confusing, and I'll try to illustrate it by a few examples. Now, maybe I always... So I noticed that this overhead projector only fits half of the slide, but I'll put it afterwards there, and normally we don't have to see more than half of it at every given time. So I like to start with this quote of Poincaré. And he said that it's very hard, one can very hardly give a satisfactory definition of mathematical probability. And you know, with these quotes, often people are quoted with things they never said, but here I really checked it, and it's written in his book. And probably one of the reasons for that is that probability appears a lot in real life. And I've written here some examples where it appears. So it appears in gambling, it appears in insurance, in genetics, in statistical physics, where you cannot even make the basic definitions without the notion of probability. So maybe that's the reason why it's so difficult to give a satisfactory definition, because usually we meet this notion of probability long before we see it as a mathematical object, and then we may have some preconception about it, which is not necessarily consistent with the mathematical definition. If we still have to give some definition of mathematical probability, then we would probably describe it as a mathematical theory of uncertainty. Okay. Now, usually, let me put it here. It is common to say or think that as a formal theory, probability started in the 17th century with a letter correspondence between Blaise Pascal and Pierre Fermat. They were motivated by a question of another Frenchman, Demar, about splitting the bets in an unfinished cube game. But then for the rigorous theory, one had to wait to the development of measure theory in the beginning of the 20th century. This was the thesis of Lebesgue. And this enabled Kolmogorov in the 30s to really define the basic concept of probability, a random variable, a sample space, expectation, variance. You need the notion of an integral there. And today, probably it will be fair to say that probability is an important topic in mathematical analysis. And as I said, what I want to try to show you at the beginning are some examples where probabilistic thinking is misleading or maybe confusing. And let me start with this story of a game called Let's Make a Deal, or the Monty Hall game, after the name of the host. Incidentally, I'm assuming that you can hear me in the back also, but if you don't, then just scream. Okay. So what you see here is a picture of Merlin Vos Savant. She's writing in Parade magazine, and she also writes for several other periodicals in America, and she also has a segment in CBS TV, and it's called Ask Merlin. So she's listed in the Guinness Book of World Records as the human being with the highest measured IQ ever. 228 is the official number. And you can ask her everything. So including starting with problems in the marriage, let's say, and ending with questions in mathematics. And she answers everything, and usually she's pretty good on all these topics, at least the ones I can judge. Yeah, so there were some cases where she wasn't so good, and indeed Fermat's theorem or Wiles proof was one of them, but usually she's pretty good. And someone asked her about this probability puzzle that is called Let's Make a Deal, or the Monty Hall game. And that's a famous game show that was in TV. And it goes as follows. So let me try to illustrate it here. So there is this competitor, and then someone, Montyhall, was usually the host of this game for many years. And this competitor is on the stage, and he has 3 doors, as you see here. And behind one of the doors, there is a big monetary word. And he has to guess it. And if he guesses it right, then he gets the money behind the door. And if he guesses wrong, then basically he gets nothing. But to make it more impressive, usually they put behind the other 2 doors a donkey, let's say. So just something that illustrates that this is not so good. So let's say that here is the attempt to guess the door. So the guy is guessing this door. And then the host, always, what he does is that he opens one of the other 2 doors. You see, no matter what this guess was, because this big word is only behind one of the doors, then among these 2 doors that were not chosen, at least one of them has a donkey behind it. And therefore, the host, what he can do is he can open that door. And that's what he does here. And he shows him that this door is not good. And in view of this, the question to the competitor is, do you want to switch doors? So he chose this. Now we know that this big money is either here or here. And the question is, do you want to switch? Now you see, the word was behind some random door, and therefore it seems that now we have 2 doors, and therefore with probability 1/2 it is here, with probability 1/2 it is there, and therefore maybe it makes no sense to switch, or it wouldn't matter if you switch or not. And indeed, let's say that in this case he decides not to switch, and we can then open it and see that in this case he loses, right? And the question is, and this is what people ask Merlin was savant, is should you switch in this case or not? In fact, here, so as I said, it's confusing, but it's not so difficult to see that in fact you should switch. Because you see, if your strategy is always to switch, then you will get this big money word if and only if you didn't choose it right at the beginning. And therefore, it means that the conditional probability after the second door is open, the conditional probability that the word is in the door you didn't choose is 2/3. And therefore, it's 2/3 and 1/3, and you should switch. In fact, what Merlin wrote was a short answer to this question, and she wrote the correct answer that indeed you should switch. She explained it briefly. And then about a month later, she wrote another longer article, because it turns out that a lot of the readers didn't believe it. And they asked why, well, it's confusing. And they tried to explain that this is 1/2 and 1/2. So she wrote a somewhat longer article explaining it in details, why you should switch. And then about 2-3 months later, she really published a very long article about this, because it turned out that people still didn't believe her. And then she got lots of letters, including letters from professional mathematicians, usually from small colleges, and they wrote her with their names and affiliations. And some of these letters were pretty insulting, like saying that why can't you admit that you were wrong? And we always knew that women cannot understand mathematics and things like that. And she published it together with the names and affiliations of these people and explaining. But anyway, this is just to say that it can be confusing. And so maybe I leave this here. But that one is not so bad. Let me try to give you another still light example, because before we get a bit more technical. And here I just want to tell you the problem, and I won't tell you the answer, so you can think about it. And that's some sort of a game. And we'll call this game, let's say, picking the right envelope, like this. So here is the way we play this game. So I'm going to choose, with probability 1/2 to the I, I'm choosing 2 numbers, 10 to the I and 10 to the I plus 1, and then I write them in sealed envelopes. So it means with probability 1/2, the numbers I'm choosing are 10 and 100. With probability a quarter, the numbers are 100 and 1,000. And with probability 1/8, it's 1,000, 10,000, and so on. Okay, so once I made this choice, then I'm writing these numbers 10 to the I and 10 to the I plus 1 in sealed envelopes. And then you can pick an envelope, you open it, and this is the amount in reals, in dollars, let's say in reals, that you get. Okay, but before you get it, I ask you if you want to switch the envelope. So imagine that you open this envelope and you see that what's written there is 10. Well, if what's written is 10, then with probability 1, what is written in the other envelope is 100, because 10 came only with 100, right? And therefore, certainly, you should switch if your objective is to maximize the profit. Now, on the other hand, if you open your envelope and you see, let's say, 100, then you can compute the conditional probabilities. And the conditional probability, it's the right computation is written here. It's very simple. So if you see 10 to the I, then the probability, let's say you see 100, then the probability is that in the other envelope, the written number you still haven't seen is 10 to the I plus 1. This probability is 1/3. And then still, it seems, so if you see 100, then with probability 1/3, if you switch, you will get 10 times more. And with probability 2/3, you will get 10 times less. But still, at least in terms of expectation, it seems useful to switch. And therefore, it seems that it is always better to switch. So I can actually ask you if you want to switch even before you open this envelope. And it seems, according to this explanation, that you should switch. But then, in fact, I can ask you this question: do you want to switch again? And the same reasoning says that you should switch again, right? So you have this envelope, and then you switch it to the other one without opening, and then you should switch again, and so on. You will keep switching envelopes without ever opening anything. And obviously, something has to be wrong here, because if we switch the envelope an even number of times, we are back to where we started with, for example. So there should be some explanation that explains what is wrong in this reasoning. Okay, so as I say, I'm leaving this as an exercise. And let me get a little bit more technical. And I want to talk about randomized and de-randomized algorithms. So randomized algorithms are when we use probability, and de-randomized algorithms are when we have a randomized algorithm, but then we try to use some procedure to convert it into a deterministic algorithm. And it is quite common to believe, it's not known, but the common belief is that randomization does not really help in computation. Namely, the belief is that every decision problem that can be solved in polynomial time deterministically can also, that can be solved in polynomial time randomly, can also be solved in polynomial time deterministically. But still, the theme I want to stress is that even if we are interested only in deterministic algorithms, suppose we cannot at all have random coin flips, then still this probabilistic reasoning is useful. Namely, it is useful to think first about a randomized procedure and then to try to de-randomize it, to convert it into an efficient deterministic procedure. Because the claim is that in many cases this enables us to find deterministic efficient procedures that we probably wouldn't have found otherwise. So there have been several early examples of randomized efficient algorithms. There have been ones before the ones I've listed here. So like quicksort. There are some simple examples that have been found long ago. But these are maybe the first examples where it was kind of surprising that probability can be useful. And the first example I listed here is this algorithm by Elwin Berlekamp for factoring polynomials over a finite field. Then there were these two primality testing algorithms by Bob Solovey and Volker Strassen followed by a somewhat better version by Michael Rabin. So these are to test if a given large number is a prime. Why are we interested in primes? Well, so primes are, of course, very basic in mathematics. Already Euclid knew more than 2,000 years ago that there are infinitely many primes. About a few months ago, I was supposed to explain in the radio, again, this was some strange show, but I was supposed to say a few words about the definition of prime numbers. And I was telling the host what is a prime number, so I said the definition. They said that already Euclid knew more than 2,000 years ago that there are infinitely many primes. And the host immediately asked me, and today, are there still infinitely many primes? So right away I understood that I couldn't go very far in this show. But anyway, primes are interesting. Very many of the old open problems in mathematics have to do with primes. You know, the twin primes, Goldbach conjecture, even the Riemann hypothesis. And here is a quote of Gauss, translated from Latin, I guess. So he says that the problem of distinguishing between prime numbers and composite numbers and the related problem of factoring composite numbers and finding their prime decompositions are very important in arithmetic. And then he describes some of the usual methods to try to do it. And he says that these methods do not really apply, are not efficient for large numbers. Of course, at that time, there was no real definition of efficient algorithms, but still people knew what this means. So people have been interested for a while about deciding if numbers are primes, and then there were these very efficient algorithms. Now, what is good about primes? So big primes are useful in cryptography. Probably many of you heard about, say, the RSA crypto system. But let me try to give a kind of a simpler example. So that's, again, an example of a probabilistic protocol where we can use primes, and we can't see them together maybe here, but let's do it here. So the claim is that primes are useful in cryptography. And what we see here is a story of Bob and Alice. So Bob and Alice were married. And then at some point they got divorced. And they, let's say, Bob went to California and Alice stayed in New York. And then they wanted to divide the property between them. So they agreed on everything, basically, but then they still didn't decide about the car. So the car is still there. They don't want to sell it and split the money. They want to decide randomly who gets the car. Now, they still talk with each other, but they prefer to do it over the phone. So they don't like to meet anymore. And anyway, Bob is in California, I said, and Alice is in New York. So they want basically to flip a coin over the phone. So you see that Bob here is calling Alice, and then maybe he's throwing a coin, and he's asking her heads or tails. And she maybe says heads, and he can say, sorry, that's tails, I have the car. Well, of course, she's not that dumb. So they need to find some protocol that will enable them to really flip a coin over the phone. And here is one way to do it. So you see that Bob will ask Alice a question of the following type. Is this number 2,478,913, is it a product of 2 primes or a product of 3 primes? Of course, once she sees that, she remembers why she divorced him. Always an annoying person. But so they are going to do it, of course, with bigger numbers. So let's say they are going to do it with numbers of about 500 decimal digits. And you see that Bob here, once he is asking this question, he is looking at his watch and he is measuring time. She has to answer, let's say, in 30 seconds. Now, the way he does it is that he decides randomly if he wants to take a product of 2 primes or a product of 3 primes. And then because of these efficient algorithms, he can generate these big primes quickly, check that they are primes, multiply them, send it to her. There is no way, or at least we don't know any efficient algorithm, randomized or deterministic, to decide quickly if a big number is a product of 2 primes or a product of 3 primes, and therefore she will have to guess. I mean, like you can see in this example, we can do it easily by computer, but of course it's hard to do it by hand. That's actually a product of 3 primes. So she will have to guess. Once she guesses, he tells her what's the correct answer, and he actually gives her the prime factorization. And she can check again that the numbers he gives her are primes, that indeed the product is the right product. So she can check that he didn't cheat. So that's one reason why we want to have big primes. So as I said, there was this algorithm of Solovey-Strassen. There was another version by Rabin. Here is a more recent version, almost including the proof of it. So that's a more recent, still randomized algorithm by Manindra Agrawal and Somenas Biswas. That's a few years ago. So they need the following lemma, which is not difficult to prove at all. And it says the following. So suppose p is a number, not necessarily a prime, just an integer. And if you take a number that is relatively prime to p, they don't have any common divisor, then this polynomial identity that x minus a raised to the power p is equal to x to the p minus a modulo p, this holds if and only if p is a prime. You just use the binomial expansion, and then you have to compute some divisibility of binomial coefficients by some prime, and there is some simple way to do it. Okay. So we want to use this to design some algorithm for testing if number is a prime. Now you see it's difficult. This number p is big. It's now a number with 100 decimal digits, let's say. We cannot really compute x minus a to the p modulo p, because that's a polynomial of degree p. It has p different coefficients. Just to write it down, we'll have to write down 10 to the 100 different things. There is no way we can do it in reasonable time. So how can we do it randomly? Well, there is a simple randomized algorithm that does it. Instead of computing it precisely, we compute it modulo a randomly chosen low degree polynomial. So what we do is that first there is this technical point that we have to check if a is a proper factor of another integer. That can be done quickly by some sort of binary search. And then what we do is that several times we take randomly a polynomial of degree something like log of the number we are trying to decide if it's a prime or not. And then we make all this computation modulo p and also modulo this polynomial. Then it's easy to compute it quickly because we compute the high power by squaring it several times, and whenever we square it, we take it modulo this polynomial. It will not have too many coefficients. We can write it down, we can do all the computation, and then we can show, and it's not difficult, that if this equality, if this equality here does not hold, then the difference between these two polynomials is not a zero polynomial, and therefore it cannot be divisible by too many irreducible polynomials. Now, when we take a random polynomial here, then with reasonable probability it is irreducible. And because this difference is not divisible by many of them, then we'll find with high probability some polynomial such that the difference is not divisible by it. And this is supposed to convince us that if indeed the number is not a prime, namely this polynomial is not equal to this polynomial, then we are very likely to actually find it. And indeed, doing it with all the detailed proof, we just need another 10 or 15 minutes, so I'll not explain it, but it's not difficult. And that's this randomized algorithm. So, so I have here this transparency about the conflict between kind of modern randomized algorithms and classical mathematics. So you see here this child with a PC, and he is running this randomized algorithm, and he's saying that 2 to the 400 minus 593 is a prime. That's actually correct. That's the largest prime that is smaller than 2 to the 400, the largest number that is smaller than 2 to the 400 and is a prime. And then Gauss, who is representing here classical mathematics, is asking, are you sure? I mean, it's randomized after all, and you can't be sure. And this guy is answering, and he's also right, do you want to bet? I mean, the fact is that we can run this randomized algorithm several times, and we can make sure that the probability of an error is so low, is like 2 to the minus 1,000, let's say, which is probably lower than the probability of making a mistake in any rigorous mathematical proof. So that's about randomized algorithms. Now then there was a quite exciting development about almost a year ago, and that was again by Manindra Agrawal and 2 of his students, Yuraj Kayal and Nitin Saxena. So what they found is actually a deterministic algorithm for testing if a number is a prime. And as you see, this algorithm is very similar to the randomized algorithms that they had before. So it's really a conversion of that algorithm into a deterministic one. So here is a deterministic simple primality testing algorithm. Here the proof is not quite simple, so it uses at least one relatively deep fact in number theory, and then it uses some clever ideas. But the algorithm is very simple to describe. So again, as before, you first check if the given number p that you want to check if it's a prime or not, if it's a proper power of an integer. Well, of course, if it is, then it's not a prime. And if it is not, then what you do is that you don't do anything random anymore. You just check for every small integer r. So that will be still something that is polynomial in the size of the representation of the number, or something that is really efficient for reasonably small numbers, I mean like 100, 200, or 1,000 digits. So for every small number r, and for every relatively small integer a, you check if x minus a to the p is equal to x to the p minus a modulo p, and also modulo this polynomial here, x to the r minus 1. Okay? And now, if always this is the case, this holds as equality, then for sure the number is prime, otherwise it is composite. Now you see that it's almost exactly what we see here. The only difference is that instead of taking the number a randomly, we now take all the small numbers a and check them. And instead of taking the polynomials qi of x, the low degree polynomials randomly, we take some specific polynomials, x to the r minus 1. And then it turns out that you can prove that that's enough. So this is supposed to illustrate the theme I told you that I want to stress, that even if what we want to find are deterministic algorithms, then it's very helpful to start with randomized ones that are pretty simple to find, and then to try and find a way to convert them into deterministic algorithms. Now, I must add that some people, usually number theorists, who know already this algorithm, they somehow don't feel that this algorithm is indeed a de-randomized version of the probabilistic algorithm, but definitely Agrawal himself, because I heard it from him, and these guys definitely think about this as a de-randomized version of the randomized algorithm he had before. And I think that's indeed a good way to think about it. And indeed, was not so easy in this case. So it took some 2-3 years to find this deterministic version. So one needs some new ideas, but still it really helps to have still the randomized version. Let me give you another example of maybe less spectacular, but maybe it illustrates better the points that thinking probabilistically is helpful. So that's an example of something we call color coding. That's now an algorithmic or computational question in discrete mathematics, in graph algorithms. That was questioned by two computer scientists, Christos Papadimitriou and Mihalis Yannakakis. And what they were asking is, can you decide, given a graph on n vertices, can you decide quickly, let's say in polynomial time, if this graph contains a path, just a simple path, consisting of exactly the integer part of log base 2 of n vertices? Okay, so pretty long, but not that long. Can we do it? And it turns out that the answer is yes. This was together with Rafi Uster and Uri Zwig. And let me tell you how this goes. So again, it's an example of something that you start with a randomized algorithm, and then you convert it into a deterministic one. And again, without all the details, but it basically fits in one slide. So here is how the randomized version goes. So k will be this length of the path we are looking at, right? The log base 2 of n. And when we are looking for a path of length k, then what we first do as a randomized algorithm is that we color the vertices of this graph randomly by k colors. And then we are looking for a copy of this path, which is a multicolored copy, namely a copy of the path in which no two vertices have the same color. Every color appears exactly once. Okay, like the path that you see here, no two vertices have the same color. And it turns out that it's not difficult to decide if there is such a path using some sort of dynamic programming. So basically, you do something which is quite simple. And then an easy computation tells you that if you color randomly the vertices, and if there is a path of length k, then with probability about 1 over e to the k, that would follow from Stirling's formula, with probability about 1 over e to the k, this path would be multicolored. So if you repeat this thing an exponential number of times, and exponential in k is still polynomial in n, right, because it's e raised to the power log base 2 of n, so then if there is a path, it is likely to become multicolored, and then you will find it. But we want actually a deterministic algorithm, so let's convert it into a deterministic algorithm. And it turns out that it's possible. So it's possible to do it using what's called the perfect hash functions. So there are some efficient procedures that tell us how to define a not too large number of ways to color n vertices. So it will be a polynomial number of ways to color n vertices by k colors, so that the following would hold: for every set of k of the vertices, in at least one of these colorings, and in fact in many of them, but in at least one, it will be multicolored. So there is this way of doing it. And then the algorithm is very simple, right? So we will just use all these ways to color the vertices, and for each coloring, we'll use this dynamic programming type thing to check if there is a multi-colored path. And again, if you look, let me again stress the fact that, again, the main theme here is that we had to start randomly and to convert it into a deterministic procedure, because if you look, for example, at the code of this algorithm, it would do very strange things. So it would start by all kinds of computations of polynomials over some finite fields. We'll do a lot of modular computations, which have basically to do with these perfect hash functions. And all these computations will have nothing to do with the graph. So this is all done beforehand. And then once you have these computations, then you start looking at the graph and do this other part of the algorithm. So then it looks like something that would be very difficult to find without having a randomized version first, but not too difficult to find if we start from a randomized procedure and then convert it into a deterministic one. Okay, so let me leave these algorithms and talk a little bit about what is called in discrete mathematics the probabilistic method. So various researchers realized more than 50 years ago that probabilistic reasoning can be very effective in the proofs of purely deterministic statements. And there were examples in analysis, in number theory, in geometry, but probably the most striking examples were in discrete mathematics, where the method turned out to be a very powerful technique, and it's now called the probabilistic method. In one sentence, this is what it does. And this looks very naive, so it's surprising before you see some examples that this indeed is helpful in proving anything useful. So when we try to prove that a certain combinatorial structure or substructure of a given structure exists, then what we do is that we construct a sample space of candidate structures and show that a randomly chosen point in this sample space has all the desired properties with positive probability, and therefore this thing exists. And I also have here a picture of Paul Erdős, who is not only the inventor of the method, but certainly contributed to its development and its application in combinatorics, in graph theory, in combinatorial number theory, and in combinatorial geometry more than anyone else. So I'll just give you one area in which these probabilistic methods have been very useful, and that's what's called the Ramsey theory. So very informally, what Ramsey theory says is that every sufficiently large system contains a pretty large subsystem which is very well organized. Or even less informally, the way that Motzkin put it is that complete chaos or complete disorder is impossible. Although you sometimes get the impression in life that that's not quite right, but still in mathematics it turns out that this holds in great generality. So there are really lots of mathematical structures to which this can be applied, and I've written here some areas in which Ramsey theory has been applied. So there are, of course, lots of applications in combinatorics and graph theory. I'll mention some. Then there were early applications in number theory by van der Waerden, even before that by Schur and by Hilbert. Then there are applications in functional analysis, something like Dvoretsky theorem, and basically results in what's called the local theory of Banach spaces when we are dealing with finite dimensional norm spaces. There are applications in game theory, especially in the theory of repeated games. Then there are lots of examples in theoretical computer science, mostly in proofs of lower bounds for the complexity of various computational problems in various models. And then there are some geometric examples, mostly in combinatorial geometry. An early example was by Erdős and Szekeres, but then there are others. So it really appears in a lot of areas. And let me tell you an example in graph theory. That's essentially the original statement of Ramsey's theorem. Actually, it's a special case. So we want to define here, we are given a finite collection of finite graphs, h1 up to hk, and we define the Ramsey number r of h1 up to hk. That will be the smallest, the minimum number n, if it exists, such that whenever we have the complete graph on n vertices, n points, and every two of them are connected by an edge, and we color them by k colors, then in one of the colors, we must always find a monochromatic copy of this graph hi in color number I. So you see that that's the basic logic behind all these Ramsey theorems. If we have a big system, then we have a well-organized subsystem. Here, well-organized means that all the edges of this copy of hi have the same color. So it's as organized as it can be if we are looking at the copy of hi. They all have the same color. And here is an example saying that the Ramsey number of a triangle, if we are using two colors and we start with 6 vertices, then no matter how we color the edges by 2 colors, there will always be a monochromatic triangle. And the picture here shows that 5 vertices are not enough. Here you see the coloring of the edges of a complete graph on 5 vertices by 2 colors, and there is no monochromatic triangle. Now, of course, this coloring can represent any symmetric relation. And in fact, a common puzzle that appears often in high school Olympiads of mathematics is that to show that among any 6 children, let's say, there are always either 3 that are mutually friends or 3 that are mutually non-friends. Because that is exactly, well, assuming that friendship is a symmetric relation, that is exactly the same as coloring the complete graph on 6 vertices by 2 colors. When 2 are friends, then we'll connect them by a blue edge. If they are not friends, we'll connect them by a red edge. So the theorem of Ramsey, actually a special case of it, but the general theorem is almost the same, is that for every finite collection of finite graphs, this Ramsey number is always finite. If we start from a big enough complete graph, we color the edges, then no matter how we do it, we'll find a copy of one of the graphs in its own color. Okay? And there is this story of a Hungarian sociologist named Sándor Szalai, who did in the 60s some experiments with groups or tests with groups of children. And he really found out that whenever you have a group of 20 or so children, then always either there are 4 of them that are mutually friends or 4 of them that are mutually non-friends. And you can see how one can try to draw some behavioral consequences out of this. Friendship tends to be transitive and so on, which seems indeed logical, but actually that's a mathematical fact and not a sociological fact. Because indeed, this Ramsey theorem tells you that the Ramsey number of K4 is 18. Whenever you have 18 or more children, always there will be 4 of them that are either mutually friends or 4 of them that are mutually non-friends. And you cannot draw any behavioral consequences out of this, just as you cannot draw any biological consequences from the fact that among any 3 normal people, 2 will have the same sex, right? It's just a mathematical fact, has nothing to do with sociology or biology. Now, we should add that actually this Sándor Szalai, he suspected that that is a mathematical fact, And he talked with some of his mathematical friends, and Vera Schoch, who is a combinatorialist, told him about Ramsey theory, and he became very interested. He actually tried to find some bound for this Ramsey theorem for K3, 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 for colors, and so on. Anyway, these numbers, although they are all finite by Ramsey theorem, they are very difficult to find. So as I told you here, R of K4, K4 is 18, but R of K5, K5, for example, is not known. It's known that it's between 43 and 49, but the precise number is not known, and is too big to check all the possibilities by computer. Now, we are more interested in asymptotics. How do these numbers behave? And in the study of these Ramsey numbers, probabilistic methods have been very useful. So here is the basic diagonal Ramsey number. How large should be a complete graph if we want that no matter how we color the edges by two colors, we'll find a monochromatic copy of a complete graph on k vertices? So the upper bound that was known for a while was proved explicitly by Erdős and Szekeres, but actually a similar bound follows from the original proof of Ramsey, was about 4 to the k. And for quite some time, people like Turan and others believed that this number is much smaller, that it's polynomial in k. And then Erdős published a very short article, 2.5-page article in the Bulletin of the American Mathematical Society that was in 47. And there he showed that the exponential behavior is actually the truth. That really the lower bound is something like 2 to the k over 2. And the proof is probabilistic. And really, today, we can say the proof in 2 words. Namely, the proof is we color random. We just take a complete graph on 2 to the k over 2 vertices. For each pair of vertices, randomly and independently, we flip a coin. With probability half, we color it red. With probability half, we color it blue. We do some simple computation, and it turns out that with positive probability, there will be no monochromatic complete graph on k vertices, and therefore such a coloring exists. And I should add that actually it's not known how to find such a coloring explicitly. And explicitly, let's say, it means efficiently. So we want to do it by an algorithm that runs in time polynomial in the size of the coloring that we are constructing. So we don't know really to describe such a coloring. We only know, and it's very easy, to prove that it exists. So there are very few interesting or non-trivial families of graphs for which the behavior of these Ramsey numbers is known, at least up to a constant factor. And I give you here a few examples. So the first interesting example is the Ramsey number when we are using 2 colors, and we ask how big should the complete graph be if we want to either get a monochromatic, let's say, red triangle or blue complete graph on t vertices. And it turns out that here the correct behavior of the size of the complete graph you start with is something like t squared over log t, up to a constant. And the upper bound was proved by Aitai, Komrosh, and Semredi. The lower bound was proved by a few years later by Jeong, Han, Kim. And both bounds make heavy use of probabilistic arguments. The upper bound is using something that's called the semi-random method, or Redel's nibble. And the lower bound makes some heavy use of large deviation inequalities, and especially inequalities proved using martingales. Here is another example, and that's proved by some combination of probabilistic arguments and some spectral techniques or algebraic techniques that have something to do with the connection between eigenvalues of matrices associated with graphs and their structural properties. And here I just wrote one example, or one family of examples. So if we want to know how big should a complete graph be, so that if we color the edges by 4 colors in this example, then we either get a cycle of length 4, a square, in one of the first 3 colors, or a complete graph of size t in the last color, Then it turns out that up to a constant, that behaves like t squared over log square t. Okay? It's again something that we know up to some constant factor. And as I wrote here, it's still not known what is happening if we are only using two colors. And we want to either get a cycle of length 4 in the first color or a complete graph of size t in the second color. That was, in fact, a question mentioned by Erdős in his ICM lecture in Warsaw in '83. And it's still as open as it was, but at least we understand better what is happening with more colors. Here is another example that follows from essentially the same. Let's put it here. That if we are using 3 colors and we want to either get a triangle in one of the first 2 colors or get a complete graph of size t in the last color, then essentially it behaves like t cubed up to some polylogarithmic factor. And there are several other examples. As I said, for many other examples, we have no idea how these things really behave, or there are bounds that are pretty far from each other. Let me just use the last 3 minutes or so to say something about explicit constructions. So this was about probabilistic proofs. Sometimes we want to describe them explicitly. And by explicit, we mean, as I said, efficiently. So an explicit construction of a structure is something that we can construct in time polynomial in the size of the structure. And sometimes these constructions are used for de-randomization. So we want to convert randomized algorithms into deterministic ones. We need some pseudo-looking combinatorial structures or graphs. And since we want to use it for deterministic things, we can't construct them randomly. We need some explicit construction. So here are a few things about explicit constructions of Ramsey graphs, of colorings, like the colorings I was talking about. So remember that, as I mentioned, for the original Ramsey number R of k, the correct behavior is exponential in k. The best known explicit construction is due to Frankel-Wilson. This basically behaves like k to the roughly 1/4 log k over log log k. So it uses some set intersection examples. And here is some more complicated construction that's with Pavel Pudlak. And suppose that we don't want a complete graph of size k, but k is fixed now in one of the colors, and we don't want a complete graph of size t in the second color, then still we can get by an explicit description something that at least grows more than any polynomial in t. And here I just want to show you very quickly, but this is just in order to mention the relevant buzzwords, something about this explicit construction, because as is pretty typical for those, it uses tools from several areas of mathematics. So the description is given here. We start with a finite field with q to the r elements, and the vertices of our graphs are subsets of a certain size S of the field. Afterwards, we choose the right parameters, so that for every 2 distinct elements of this subset, the norm of their sum over the small field, and the norm of an element of the big field over the small field, is when you take this element and you raise it to the power q to the r minus 1 over q minus 1. So that's what is written here. If the norm of every sum is 1, then that's a vertex. And then there is a similar condition that tells us when we color 2 such vertices red, if there is an element in A minus B and an element in B minus A, such that the norm of their sum is 1. And what comes into the proof that this has the right property? So there are some spectral techniques. So as I mentioned already, there are some things that relate some eigenvalues properties of matrices associated with graphs. And here we look not at this graph, but some graph associated with it, and the structural properties of the graph. Then the graphs we are looking at are some Cayley graphs, and in that case, the eigenvalues can be expressed in terms of character sums. So one needs some character sum estimates. And here one thing that can be used is Veil theorem, the Riemann hypothesis for curves over a finite field. One can use some more sophisticated results of Deligne to get some sharper estimates, but it won't change much here in the end result. Then there is something from algebraic geometry, really a result of Kolar, Ronya, and Szabo, that has to be used to prove another property of this graph. And then there are two combinatorial results. One is on what's called the Zarankiewicz problem, and something about what's called a delta system. So this slide was not supposed to make too much sense, but just to say that one has to use a lot of tools. And let me just finish by saying do we really need this probability? So I already told you at the beginning that the common belief is, although that's not known, that every computational problem that can be solved probabilistically efficiently can also be solved deterministically efficiently. And therefore, the belief is that probability really does not help there. But I think the main ideas I was trying to convey is that probabilistic reasoning or thinking probabilistically does help. So it does help even in finding deterministic algorithms, and it does help in proving deterministic statements. And if we think about this as probabilistic reasoning, then I'm convinced that this will keep playing a major role in the development of discrete mathematics and of theoretical computer science in the future as well. And with this, let me finish and thank you for your attention.